I recording? Yeah. All right, my friends. Final homework. Due next Monday. We will definitely meet next Monday. We're going to get through all the stuff I would ever hope to get through into this class and have a little bit extra space. So that's so cool. What I'm planning on is when we come back from break that Monday, giving you the take-home final that day. And then maybe some of the stuff that is on there we'll still have to talk about on Monday and Wednesday, but hopefully just Monday. And then giving you, at least at a minimum, that Wednesday, that last Wednesday we have together to work together and talk about and consult. And then I'll have office hours finals week, and it'll be due at the end of finals week.
So we don't have to come to our scheduled finals.
When is that?
On Friday at 10:10.
I would never go to a Friday final,
Thank you.
and I would never expect you to.
It's after two we're talking about.
This is, I would do 8 a.m. finals, and it's like if I see there's an 8 a.m. finals, like take home final. Absolutely, that's what that means to me.
Yeah.
Translates.
No, if I ever be a college teacher, my first classes will always be earliest at 11 a.m.
There you go.
Because that's when I can reliably be at school.
I'm gonna ask whatever.
I don't know. Maybe one day I'll be able to drive better.
Well, for me,
To that point. Anyway.
Anyway, hi friends. Complex analysis. See. Look. All right. Terrible pun day. So, last homework. I would love to get it next Monday, because that's the last day I'll be on campus until the following Monday. It's not too bad. Absolutely. I think by the end of today, you'll have everything you need to know to rock that homework completely.
When we're done with that, what else am I going to use to procrastinate?
Okay, I'll give you a list.
Great. Just like things I need to do is first on the list.
What are you trying to do here, Noah? Why are you derailing?
Didn't take meds today. I feel like cooperating.
Yeah, I can tell. You're troublesome today. All right. Okay, so quick review, but also an extra new fact that I didn't remember to mention. If we have an analytic function, a function that's analytic at a particular point, we can create a Taylor series at that point. So that's Z naught. I can create a Taylor series that is valid in some disk around Z naught. The size of that disk, in Calc 2, you go through and you have to compute these. You do the root test or the ratio test to compute the radius of convergence. Awesome tip. The radius of convergence will be the distance from the center to the nearest singularity. So if I had a singularity right here, and what I mean by singularity is a point of non-analyticity. Indeed. So nearest non-analytic point. And division by 0, that kind of stuff. That is what I'm really talking about here. Here's non-analytic point. That's your radius of convergence. So just a cool little fact about it. For example, let's see here. What if I had f of z equals 1 over 1 minus z? Nice classic low-level singularity. If I do a Taylor series of this at 0, what is the Taylor series at 0?
Just Z plus.
Z's in there.
Yeah. 1 plus Z plus Z squared.
Yeah, there we go. It's the geometric.
Yeah.
Right, so one of the things, there's two things you want to keep in mind for today. And one is this formula, so let's put these up. We need this rhythm. this rhythm, which is just, it's just nice to just know it as opposed to having to rebuild it every time. This one is alternating, but the same power structure. Two great things to know for today. So we can take, you will know these by heart within the next few days. So we can just pull this out, and I can say, oh, what's the radius of convergence here? Well, the center's at 0. Where's the nearest trouble spot? 1, right? So at z equals 1, I got trouble. So how far can I move? 1 unit. I've now got my radius of convergence, r equals 1, because that's the distance from the center to the nearest blow up. So we don't have to go through and crank it out the painful ways that there are to do that. What we are talking about today is what happens when the series is non-analytic at a point. What if I wanted to take this series and expand it around the trouble spot? That's what today is all about. And that's a new kind of series that I alluded to at the end of class last time, called the Laurent Series. So I got a little Frenchy there, right? Kind of like Laurent. So if f of z is has, and we're going to talk about this in a minute, a singularity, an isolated singularity at z equals z naught, we can create a Laurent series. No apostrophe. Laurent series. I'm used to that L'Hopital stuff, I guess. Laurent series about z equals z naught that is valid in an annulus, or an annular region. About z naught. So what do I mean by an annular region? I mean something like this. We're going to have a little r, and then we're going to have z minus z naught, and then we're going to have a big R. So this is saying the distance between z and the center is greater than r. So if that's z naught, then to even be in this thing here, I have to move at least r units away, little r units away. So I've got this inner radius of little r, nothing's in there, and I can extend out to the big R. So it looks like a little donut. And it's all this stuff inside here. So instead of a disk, like over there, here we get a punctured disc, or a disc with a whole other disc cut out of the center. Sometimes it's a point, sometimes it's a disc. The key thing is we want to stay away from the singularity. And in some ways it's a matter of taste as to how far away from there we stay. And this will all make a little bit more sense by the end of the hour. That is my greatest hope. So let's talk about singularities. And hopefully you kind of read a little bit. What does it mean to be an isolated point? I'm going to leave those guys up. What is an isolated point? I'm an ice chewer too. Way back.
Isolated point or isolated singularity?
Pick which one you want. I was going to try to get us there slowly, but
It's if there exists some deleted neighborhood or punctured open disk of z naught throughout which f is analytic.
right
Like
on.
between 0 and where z minus z naught is between 0 and r.
Right on. That sounds good to me. So an isolated singularity. Let's just talk about singularities for a second. So we have a little bit of vocabulary. An isolated singularity is a trouble spot, like maybe here at 0, where there's no other trouble spots in an open region around that troublesome area. So for this one, if I remove 0, and that's my singularity, it's not analytic there because division by 0 isn't defined. 0 isn't even in the domain, so it can't be analytic at 0. Here we have a singularity, and there's no other singularities nearby. No matter how big this disk goes, it's all good. So it's all kosher everywhere else. No bad stuff. What about this guy? Where are the singularities there? 1 and 0. So we've got trouble at 0, we've got trouble at 1, but these are both isolated because I can just put a little disk around that one and there's no other singularities in here. This is an isolated singularity because there's a little disk where everything's kosher away from it. It doesn't matter how far, as long as there's some distance, positive distance I can move away and everything's okay, that's an isolated singularity. Let's take a look at,
So,
yes, go ahead, Noah.
The singularities only essentially happen at 1/0.
Yeah, for the most part, except for something like logarithm, where we have that mess that happens here on the negative, positive, or the negative and negative real axis, the non-positive real axis. So something like this, the principal log, that has singularities at 0 and then along this entire negative axis. Here's another one. If I take a look at sine of 1/z, that's a real mess. That's a serious mess. Now let's think about why that's a serious mess. Because,
I thought sine was.
actually, that just has a single, yeah, let's do this.
Oh yeah,
There we go.
oh yeah.
There we go. That's a mess. So
That
why is that a mess?
Just put it on.
Just keep putting, no, one more. No, it's just, but this will do it. So if we take this guy right here, where is this gonna be a trouble? So this has trouble when sine of 1/z equals 0.
Also at infinity.
And at infinity, yes. But we don't consider that generally part of our singularities.
No, I mean when z is equal to 0.
Yes, wait, I'm sorry, come back, are we talking about over here,
No,
Noah?
I'm talking about,
Oh, this guy here?
yes, when z
Okay.
equals 0, it's sine of infinity.
Yes.
Or sine of something.
Yeah,
Not really.
serious, yeah, so 0 is a serious
So
messed
yeah,
up point.
0 is a messed up point at any point where sine is equal to 0. Yeah,
Yes,
okay, point.
indeed. So we have trouble when this happens, and also at z equals 0, so for sure. And so my question is z equals 0 an isolated singularity? So is this isolated? Because clearly it is a trouble spot.
No.
Well, no, because sine of z, this equals 0 if and only if 1/z equals what? When does sine of z equal 0? When does sine of something, what does the argument have to be to give you 0? What's in the box?
Pi k.
A multiple of pi, right? An integral multiple of pi. So if 1/z equals k pi, and here k can be any integer, probably should take out 0. Let's just do that. If we have that, that means z is 1/k pi. Each one of those is going to be a place where this bottom goes to 0. And so they're all singularities. What do they look like? So when I look at the singularities in the complex plane, they're all going to be points on the real line. So we know 0's a rotten spot. We knew that. But then I've got 1/pi. which is like a third. So that's a bad spot. I've got 1 over 2 pi. That's right here, halfway. That's a bad spot. I've got 1 over 3 pi, 1 over 4 pi, 1 over 5 pi. And what I actually have is a cascade of singularities accumulating at 0. So 0 is an accumulation point for the singularities that are produced this way, but they just start grouping up. And what I'm claiming is that there is no neighborhood around 0. Each one of these, how about this? Each of these is isolated. Each of these singularities is isolated because you can find a neighborhood around them. Even inside here, when they're super close and you're down here and you're like, I'm at 1 over Google pi. Right there, and there's 0, so they're sitting right there. Well, the next one's still got a little space. I can still make a tiny little neighborhood around that that doesn't hit the next one or the one before. So these are isolated, but 0 is not isolated because if I make any neighborhood around 0, so let's say I make that delta, all I have to do is pick k to be a large enough integer, and these multiples of 1 over k pi will eventually be inside there. No matter how tiny that disk is, 1 over k pi will eventually fall in there as k gets bigger and bigger, and 1 over k pi gets smaller and smaller and smaller. So this is not isolated. We're not going to mess with that in Laurent series. That's a real mess. Does that make sense? What I'm getting at? Yeah? Any questions on clarification? New pen time, because good old Penny is getting dried out there. All right, so where do I want to go with that? Cool. So, how do we do these things? Well, here's the way we're not going to do it, but it's the official definition. Let me get you the whole official kit and caboodle.
I haven't heard that in a while.
Yeah, right? Yeah.
It's been a minute since
It's
I've
been
heard
a
that.
while. Do you ever hear it anywhere but my classes?
No.
Yeah.
Nope, sure don't.
Cool. Okay, cool. So if Z naught is an isolated singularity of f of z, then f can be written as a double infinite series. So here, let me show you how to kind of write this until you get used to doing it in spacing. Put the constant term right there. And then as I move to the right, it looks like a Taylor series. And as I move to the left, it looks like something new. So I'm going to have a sub negative 1 over z minus z naught. A sub negative 2 over z minus z naught squared. And then that continues on to 3 in that direction, forever and ever. It might truncate, but theoretically it could keep going that way, and it could keep going that way. Studying what this part does, this is called the principal part. So that everything with the negative powers is called the principal, with the P-A-L part. And this is called the analytic part. So in some ways, the fact that this is a singularity is reflected in this part of the series. We're going to spend a lot of time studying this in depth. Does it end? Where does it end? And one of our greatest concerns for the rest of the semester will be, what is the coefficient on that term? It will turn out that the coefficient, I'm just going to do a little foreshadowing or something, or just a hint, spoiler alert kind of. The coefficient a negative 1, right above that term, is called the residue.
Interesting.
Isn't that lovely? The residue of f at z naught.
You can just say spoiler alert whenever you say a fact.
Okay, just constantly.
Is it just the A-1 part?
Mm-hmm. Just that the number that goes on top there is going to be pivotal to moving forward. Oh, I got a couple things to get back to some friends in here. Grace, did I get yours back?
My what?
This last homework? Okay.
Oh, yeah.
Okay, cool. Alrighty, so, and then the coefficients, these A's can be found in the following way. So A sub K, where A sub K is equal to, and oh, I totally forgot it. I think it's 1 over, oh, I got it. Yay, yay, yay. I knew there was a 1 over 2 pi I because everything has got a 1 over 2 pi I in it. So an integral around a simple closed curve C that I'll define in a minute of f of s over s minus z naught to the k plus first ds. And then that formula is valid for every integer k. And C is any simple closed curve that is positively oriented around the point of singularity. So let's draw a little picture here. Here's our picture. Here's Z naught, trouble spot.
Can it contain other singularities or no?
No. No, because we're going to work only with isolated singularities, so we're always going to separate them by a region. So one at a time. We're going to have this little angular region around here. Let's see here. Put a little note down here. Sorry, I'm getting spazzed out on this. Valid for some R and R. Those are both positive numbers with little r less than z minus z naught less than big R. This is that disk, that donut that I drew there and that I drew before. So right there, that's little r. Right there, that's big R. And C is a curve that lives inside the annulus itself. So C can be any curve that just moves around the center in that domain. Like a color code. Make it a little more obvious about what I mean. We are never going to use that formula. We will never use that formula. Instead, we're going to learn the art and craft of generating Laurent series with those two formulas up there. And it is an art, and it is fun. So it's a new puzzle that you've never played before that takes a lot of practice. Let's get on it. Yep, oh, in my notes it says, now the fun part. Yay, cool. Because I was ready for it. I was like, blah, blah, blah. My God. So let's say I've got, I'm almost thinking I'm going to start off even simpler than we did before. So let's say f of z equals 1 over z. That is a Laurent series already. This is a Laurent series centered where?
0.
At 0. Because notice this is 1 over z minus 0. So this is already a Laurent series centered at z naught equals 0. What do you think the radius of convergence is? Infinity, right? Because there's no other singularities. So that idea still works here. I could travel as far away from 0 as I want, and I'll never encounter another division by 0 anywhere. So here, this is a Laurent series that is valid. Oh, it's like a W if you want, sure. Valid for as long as we don't touch 0, all is good. So the annular region here is literally the punctured complex plane. Good, everywhere in here. Now what if I said, let's find the series at 1. So find the series representation centered at z naught equals 1. What will be the radius of convergence?
1.
1. Center, trouble at 0, right? So I already know the radius of convergence will be 1 no matter what. I want to refresh your memory about playing this game that we started playing last time. So this is my toolkit right here. I only have these 2 tools to work with. Everything I do, I'm going to make things look like this or this. And then you know what? Let's put another one up here that we could use. Another tool. This is like a more modern tool. No, it's not really modern, but I've never used it before. We're going to start using it now. And also, the general binomial theorem. Binomial expansion, which looks like this. I'll have 1 plus something yield box to the alpha. Alpha can be a real number. So alpha, I'll put it down here so you can see it. Alpha is a real number. Is equal to, you could go through and generate the Taylor series for this and convince yourself that this is true, which is not a bad thing to do. Box, sorry. Plus alpha times alpha minus 1 over 2 factorial box squared plus alpha times alpha minus 1 times alpha minus 2 over 3 factorial alpha or box cubed, so on and so on. This can be super handy. This can be wickedly handy. In fact, maybe we'll do this both ways. So I want to find the series representation centered at z naught equals 1. This means I must force a z minus 1 into the expression. So this is all about looking at where you want to go and then doing algebraic manipulations to create those things in your series. So here, so f of z, I'm not going to change it, but I am going to just go ahead and put a z minus 1 in the bottom and then balance it so that it didn't really change at all. And if you notice that if I just actually add a 1 on there, life is good. So this is still the same function, but now I see good old z minus 1, and I'm thinking, oh yeah, that looks like this. So you can't quite see it, but I'm just putting the z minus 1 into this box here. I now have my series representation. So this is 1 plus z minus 1 plus z minus 1 squared, z minus 1 cubed. Forever and ever. I'm done. This actually doesn't have any of the kind of sexy Laurent stuff that's got the negative terms in it, or the things underneath. That's okay, because this function is totally analytic as long as z minus 1 is less than 1. And that'll keep us away from 0. Think about what this disk looks like. Here's the center of 1. Here is the disk of radius 1. We're all good. Because this is the real trouble spot right here. Okay, cool. So let's make things a little bit more interesting. I'm gonna assume you have these written. And if not, we can recall them. I smell meatloaf. Somebody eating meatloaf or something in here? It smells good.
I had a sandwich.
You have a sandwich. Oh,
I
man,
had a
this is so
sandwich.
had a sandwich.
Yeah, it's not
It
nice.
smells so good.
Wasn't me though.
Absolutely famished. Where the hell are my notes?
Interesting.
Yeah.
Huh.
Pretty tricky from
Nice. Okay, so let's take a look at another example. Here I've got 1 over z times z minus 3, that's f of z. And let's say I am asked to find the Laurent series, so two singularities first off, right, 0 and a 3. If we were to do a series centered at 0, it could only go out 3 and not touch the 3, because we don't want to have two singularities at a time. That was a good question, Noah. We're always going to make sure that that doesn't happen. So find the Laurent series valid for, and there's going to be all sorts of codes hidden in this that we need to look for. You always want to know what the domain will be, or the valid, the annular region for your Laurent series. Otherwise you can just create one, but each of these problems will have one, and it's encoding things. So what is the center?
0.
So center equals 0, because this is z minus 0 inside there. So I know that the center is 0. Cool. That means I'm just going to be doing things in terms of z. So check this out. So f of z equals 1 over z. This part's done. I'm not going to do a partial fractions expansion, because 1 over z for a Laurent series centered at 0, I'll just multiply whatever I get over here times 1 over z, and we'll be good. Now right now this might sound a little like, how do I know that? But I think hopefully this will resolve as we move through. And then I've got this thing over here. So I'm just making that first note. I didn't really do much except notice that I don't have to mess with this guy. This is what I need to turn into a series centered at 0 that is valid for z greater than 0. So right off the bat, this thing here is good in this region. As long as z isn't 0, this is valid. And as long as z isn't 3, this thing is valid. So this guy right here, I'm going to start playing with. And I'm seeking one of those two forms. Let me put the one up that I'm keeping in mind. I'm looking to make it look like this. I'm going to find out what ends up in that box. And what in that box should just be a z. So I'm going to make a -1, and then I've got 3, or a z times a multiple. Does that move make sense? Just multiply top and bottom by negative, so that I can just get a constant. So notice here, constant. That's one of the things I'm basing this all off of. I'm going to pull that negative out in front, just so I don't have to think about it. And then down here, I need a 1. So now I need a 1 there. That means I'm going to pull a 3 out. And when I do that, that becomes a 1, and this becomes z over 3. So let me stop for a second, and you can check this out. And let me know if that makes sense. It might not, yeah, makes sense. It might not be something you try yet because you haven't had a lot of experience doing this, but we'll get you that experience. Awesome, now I can apply what I know this is equal to in series form. So this is 1 over 3z. I might actually just put -1/3 on top. I kind of like that. And then this is going to be 1 plus z over 3 plus z squared over 3 squared plus z cubed over 3 cubed, blah, blah, blah. And this is valid. This thing, this series expansion, I should have put these up. This is valid for absolute value of whatever's in the box is less than 1. So this is valid for, now we already know z can't be 0. The part where z is underneath is this left part of the inequality. We're trying to keep away from where this part blows up. and then I'm gonna have z here, z over 3, because that's in the box, less than 1. So this comes from this, with z over 3 inside the box. Now, I don't want to leave it written like that, so I just multiply everything by 3. And I see that I actually met the needs of what I was asked to meet. And now I've got to just simplify this thing out. We'll have our first Laurent series. So do the multiplication of that outer term, bring it into all the inner terms. And what we have then is negative 1/3 over z minus, and then these z's will cancel and we'll just get a constant term, minus 1 over 3 squared. I like to keep the powers on because you might want to be finding a rhythm and write a general expression. So then this next one, we just cancel one of the z's and we get an extra 3 in the bottom. So we've got 1 over 3 cubed z, and then you catch the rhythm. And that's a Laurent series. That is valid on that annular region. What's the residue?
Why is it alternating plus and minus?
It ain't, thank you. Good. Oh, it should all just be minus. I brought the minus in for the negative 1/3. Thank you, Noah. Good catch. That was a aberration. Thank you, sir. Yeah.
Okay.
Yeah. So what's the residue?
Negative 1/3.
Negative 1/3. We'll have easier ways to get at that a little later, but right now let's just practice noticing it in our heads. Okay, so that's part A. Take that function, expand it for a Laurent series in that region. Part B says, now do it. Now do the same thing, but for a different region. So for the next one, now we're going to do this for z greater than 3. Again, that avoids both the singularities completely, the one at 0 and the one at 3. But it's kind of weird, right? So our region looks like this. Here's 3, circle of radius 3, and it's everything outside here. Let me show you kind of a back way and a front way into this. Just notice that this, we don't, either of these series that we had this, and we had this, and the expansions were only valid with this less than thing. But notice you can convert a less than into a greater than by taking the reciprocal of each side. Center's still at 0, so let's just make some notes here. Center equals 0, because otherwise it would say z minus something. We would see that. And this condition right here actually is this condition here. Does that make sense? So what we're going to do is play the games we've been playing, but we're going to force a 1 over z into this expression. An additional 1 over z, because we've actually already got one of them already. We've got this guy here, so I'm going to do the right again. So we've got f of z equals 1 over z. That's already part of a Laurent series centered at 0. Cool. Let's leave it and not do the work on that. And then I've got this thing here. I'm going to pull that negative out. Actually, no, I'm not. I'm going to leave it as z minus 3 for a second. Sorry. Literally nothing happening here but semantics, just kind of changing our perspective. Leave it alone, work on this. How do I force a 1 over z into this, or something over z? How could I do that? Just algebra, nothing weird, no complex analysis.
You don't want to put a z on the top is the problem.
Right. But what if I factored a z out? That would work, right? So here, let me see, what would this, if I pull an extra z out, leaves the top alone, what does that become? 1. And then what's that become? There you go, beautiful. So I'm heading there, this is great. What if I multiply both sides of this by 3? What's the right side become? 1. What's the inside become? Stuff coming together. Now I just use my formula for the 1 over 1 minus whatever and crank that out. This is what's in the box. And that expansion will be valid for whatever is in the box being less than 1, which is precisely this, which is precisely this, which is precisely this. So, come over here, and I go, all right, this is 1 over z squared times 1 plus 3 over z plus 3 squared over z squared plus 3 cubed over z cubed, blah, blah, blah. And then distribute, and we have a beautiful, beautiful Laurent series that looks like this. And then I'm going to probably rewrite it just a little bit, because I don't like these negative powers moving that way. It's just aesthetics, you know. 3 over z cubed, 3 squared over z to the 4th, blah, blah, blah. And so, equals, I like this. There we go. There is no analytic part there at all. It's all just principal part. And that's our series. What's the residue?
1. No, there's no residue.
There's 0. 0 is the residue because there's an implied this. Right? All those other terms are there, they just have zeros in front of them. More. And as I said, the more you practice this, the better you will become at it. Is there a question?
Yeah.
Yes?
What was the reasoning behind moving the 1 over z squared to the other side?
So we're looking for a series centered at 0 because this is z minus 0. So first I figure out, okay, where's the center at? So a Laurent series centered at 0, and you're not used to this yet, but it's going to involve coefficients over z. And I'm realizing this is actually already in the form of one of these things. And so I'll just incorporate it into whatever I produce after that. It's ready to roll. If this had been, Sydney, so like to contrast, if this had been z minus 1 out here, I would have to do something with this. But since it's already ready for prime time, it already looks like one of these things, I'm good to go.
Let me rephrase the question.
Yes, please.
So, the bottom line, you first have 1 over z squared plus 3 over z cubed. Yes, that part right there.
Yeah.
And then you went over another equal sign. Like, the other, keep going. No,
Keep going.
yes.
Okay, yeah.
Why did 1 over z cubed move, z squared move?
Oh, I just like my negative powers moving to the left.
Okay. Okay.
Does that make sense?
Yeah.
Because there might be, you never know, there could be like, there's a 3z and a 4z to the 5th or something over here. I just kind of like things, negatives and positives, but there ain't nothing wrong with that.
Okay.
Cool, thank you for rephrasing. Let's do some problems out of the book. Let's do another one. So this one, and this is basically the rest of what we're gonna do today. We're gonna be doing a lot of this on Wednesday because you really have to do a lot of it. I almost said a curse word. I'm gonna try to make it through the curses today. Yeah. What was that? Was that clapping because of my?
Oh no, it was just this.
Oh! It was like perfectly timed. It was perfectly timed. When the camera's off.
I guess I should make that easy on you. as opposed to difficult.
Yeah, that would be nice. Nice.
Great, I'll be a good student.
Thank you. Thank you. You have been feisty today though, so I wouldn't.
That was been on one. Well,
So here's our thing that we're gonna expand. We got z minus 1 squared, z minus 3. And part A of this problem says find the Laurent series, that's the unspoken in all of this. That is valid here.
All of there?
Yes.
Because isn't there gonna be a thing at... And
So let's draw the picture real quick, right?
Yes,
Here's
please.
1, and then I know what you're thinking, but we actually stopped shy of that terrible spot over here. Right, because this has radius 2, and then we take out the 1, that's what this part does.
oh, okay.
We get right up to it, but it's not, is that what you were worried about?
No, my brain was like, it's centered at 0 because there's a 0 there, and that's not the case.
Gotcha. Yeah. So, you know, reading the language that's here and getting used to it, because it's pretty odd and new for sure. I want to point something out that might help in this process. This is 2 conditions. This says this, and this. So this thing here, this is a normal Taylor series kind of condition. You have a center at 1, you can only go out 2, okay, blah, blah, blah. So that's Taylor series-ish. When you have this inequality, that is indicating a Laurent series. So this part right here tells me that there will be a Laurentness. This is Taylorness. So this will be for the analytic part. This will be for the principal part. Just pointing that out. Because it doesn't super help right yet, but it will. This just basically says z can't be 1. The only time this is true whenever z is not 1. And that's really all this is saying. Just don't plug 1 in, everything's good. So I have a center at 1. Cool. Is any of this ready for prime time?
no, sir.
Not at all.
Are there any z minus 1s in there?
Oh, yes, yes there are.
Indeed there are. This
That's right.
is part of a Laurent expansion already.
Yeah.
So I'm going to do the same game I did before. So this is equal to 1 over z minus 1 squared. That's you know, a term, you know, right here, kind of at that level, over the z squared stuff. And then I'm going to just worry about this part here. So here's where my work will get done. Now I need to force, so step 1 is to pull out don't do work that's already done. That's this step. Next step is force a z minus 1 into this. So this comes along for the ride, and here I'm going to force a z minus 1 in, and then I'll do the rewrite as I need. What do I have to put in here to make sure I haven't changed anything?
-2.
-2, awesome. 2, just pointing these things out. You'll see these soon. I've been practicing these all weekend to make sure I was buffed up. I was ripped. Laurent math ripped when I came in here. So this is ready for this. Let's see, we have a minus in there, so probably this guy here. But I need to switch the order. I need to have my constant be 1. And then this is going to be valid for that.
Divide by
I'm sorry, what'd you say, Noah?
divide by -2.
Yeah, divide by -2. So multiply top and bottom, or pull a -2 out, however you want to do it. I will write a negative 1/2 out in front. And then that's 1/1 minus what's left.
C minus 1/2.
Yeah. Check that out, make sure you're cool with that. Yeah.
Wouldn't you be pulling a 2 out and not a 1/2?
This 2 could be just down here too. So I'm moving the 2 out that way on the lower end of the denominator.
Got it.
That makes sense, yeah. Cool, so here's my box. This series expansion will be valid when whatever's in the box has modulus less than 1. Oh my God, when I simplify that, it's exactly what I want, right? It's popping. When you start seeing these, you're like, yes, I am doing this right, because things are matching. I'm seeing the same patterns emerge. Z can't be 0? Yeah, of course not, because this Z can't be 1. Yeah.
Good catch.
Yay.
Good?
I don't know. All right, so let's do the series. The thing in the box squared, thing in the box cubed, and we get the rhythm. Bring this piece in now, and the Laurent hood starts to manifest. So this times that is negative 1/2. Keep those constants on top. Z minus 1 squared. Here I get a cancellation, and then an extra 2 from the bottom. So this is going to be minus 1/2 squared. Z minus 1 just to the first. Make sure you see that. Dividing by 2 again, and then now I've got it. Now it's going to be these perfectly cancel, and I get a negative 1/2 cubed minus 1/2 to the 4th, and now it becomes positive at this point, because here's divided by this, but I've got more of them on top, so it's minus 1/2 to the 4th, Z minus 1, minus 1/2 to the 5th, Z minus 1 squared, minus forevermore. And that's my Laurent series. What is the residue?
Negative 1/4.
Yep, negative 4th. It's that coefficient right on top of that guy right there. So the residue at 1 is negative 1/4. I think we have one more maybe. Usually there's like 3 or 4 different ways that.
So,
Yes.
just try again. Laurent Series will always be centered at one of the singularities.
Not always. Not always, but most of the time.
Well, like, what if we wanted to center that at like 3 instead of 1?
Oh, I like the way you think. Let's just do that. I haven't pre-worked it. I don't know what's gonna happen. It's good shit.
Oh. Doctor.
Is that even a cuss word?
Well.
I was being too good of a student.
You
and
set
that's what
me up.
we-
You knew that would happen.
I didn't know.
You tricked me, Noah.
I'm sorry.
The moment you say you want to go through this day without dressing up, like, don't jinx it.
Yeah. We could try again on Wednesday.
I'll try again on Wednesday. You just pick yourself up. You carry on.
Here we go.
Well, you can
Pull
let
up
it
my
all out
pants.
before the video starts, and then
I might go through and edit that, and you'll hear like this weird like stuff.
Voiceover.
Yeah.
like snakes on a plane. When
Oh yeah.
they're clearly
Yeah.
in, Samuel L. Jackson.
Okay, so we'll have to figure this all out. Centered at z equals 3. This is Noah's question. So,
We're still doing the same like function though, right?
yes, same thing. Yeah, this beast here at yeah. Yep. well, where would this be valid? So if we had one centered at 3, 1, 2, 3, and we can't be at 3, right? So we'll put a little circle around that. So we'll puncture it at 3. How far out can I go? What should be the maximum radius I can move out? 2, exactly, because there's the next singularity. So centered at 3, so we're going to have z minus 3, and that has to be less than 2, and it has to be greater than 0 so that we can't get to 3. Cool. All right. So, is any of this serious and ready for prime time?
The one part is, but
The
not
one
the
part
square.
is, yeah. We got a z minus 3. Let's not mess that up. Old Dr. T might have said, let's not do something else to it, but I'm saying that let's not mess that up at all. That guy is a real piece of work. So we got this. Pull the piece out. Beautiful. Why would we mess with beauty? And then we have this. Cool. Now I have to force z minus 3 in to this. So we're going to do that. We got 1 over z minus 3. Oh, I love you. You're so good. And then over here, how do I get? So tell me what to write.
Z minus 3 plus 2.
That look good? Yeah, right. You literally just put in there what you want and then fix it so that you haven't changed anything. Wunderbar. All right. So, none of the stuff that we have, neither of these things look like this. Correct. Right, yeah, because they don't have squared. But there was that last thing that I gave us. And that said, let's write it out again. We had that equals blah, blah, blah. What if alpha was negative 2? So if alpha is negative 2, this looks like this. And we can use that formula to expand something that looks like this. And let me put the dang formula back up. Gosh dang it. Shucks. Well. Oh, Dr. T. One day you'll be okay. All right, so, and then that's that squared, and let's do one more. Yeah. So here we've got, we got to get a 1. Everything requires hinging off of a 1, so we need to manipulate until we get this to be a 1. How could I make a 1 here?
Divide by 1/4.
Yeah, and I would say it in a different way. I would say pull out a 1/4, right? Because we don't want to create a new division, but we will extract the 2 from inside here. When you pull the 2 out of the inside, it gets squared on the way out. So out here, I'm going to put 2 squared. I'm going to put it on top. I hope that's not confusing, but I pulled it out and I put it over here. I've got z minus 3 at the bottom. Here still. And then this becomes 1 over, and we can change the order too. This will be 1 plus z minus 3 over 2 squared. Check that out, see if that looks okay. And once we identify alpha as negative 2, we're good to roll. We just go ahead and write out, you know, two or three terms from here, probably 3. So here's what's in here. I have alpha equals negative 2. So I'm going to use the binomial expansion. I'm going to leave this piece alone. So this is 1 over 2 squared, z minus 3. And then we're going to just have 1 plus. Alpha is negative 2. What's in the box is z minus 3 over 2. Does that make sense? Yeah? Cool. And then the next one is alpha. alpha minus 1 over 2 factorial c, what's in the box, squared. And so on and so forth. Yeah, that'll be good. That'll probably be good. I think we can get the derivative from there. Last step is to distribute and see the Laurent fullness. And then, yeah, and then in your head think to yourself, the residue is, nobody say it out loud. Let's just all get to enjoy that on our own. Minus 1/2. Oh wait, wow, okay, I gotta think, there's a lot of cancellations, aren't there? So I still have minus 1/2 squared, yeah. Because the -2 and the 2 cancel, and then the z minus 3 cancels, and oh, that's just this. And then the next one's gonna be a positive, because I got -2 times -3. I cancel out a 2 from the 2 factorial. That turns into a -3, so this becomes minus 3/4.
Didn't you just say
Of
it's gonna be
positive.
positive?
Yes, I did, thank you. Yes, yes. And I'm gonna write 2 squared so I can catch rhythm. Over z minus 3. Yeah. Tell me if I got that right.
What
Did
did
I?
I times z minus 3?
I concur.
I concur as well. Thank you. Thank you. Yes.
Also, aren't you missing a 2 square?
Probably. Yeah, I feel like I didn't. Oh, yeah, because this is 2 squared here. Right. So let's see here. So this is going to be. Let's do a little work. Probably should have had another step in here of simplification. 2 squared. Oh, so we'll have an extra 2 on the bottom there, but then 2 more, so 2 cubed.
No, 2 to the 4th, because the 2's in the first term cancel,
So these. Yeah, okay.
and then the 2's
Right.
in the same term out.
I gotcha. Thank you. Like that?
Yeah,
Yeah, and is this one okay? Yeah, this one's okay.
that one's okay.
Oh, now we got pretty multiples of 2 on the power. That's lovely. And then the next one's gonna have, let's not even go there. It'll probably be negative, and then it'll be some stuff. That we can figure out if we cared,
Yeah,
and we took the time. We can figure it.
so it's good.
What is the residue?
1/4.
1/4.
Whenever you say residue, I want to hear it in like the droopy dog voice, from like Tom and Jerry.
Like, is that kind of a nasal?
Yeah, I can't do it, but it's nasally and deep with southern accent. No.
I don't even know what droopy dog sounds like, I guess.
I'll pull up his voice.
Yeah, you will.
Is imitating a southern accent when you're not southern considered not cool anymore?
Do they care what the South thinks?
Oh, ouch! Ouch, at least you're off
I
camera.
mean-
You're off camera, you will avoid.
I mean, it's not the worst thing I've ever heard come out of those mouth.
Sydney cannot even wait till leaving. Oh, I thought you were like, that's it.
No, see,
My new end of class is 2:12.
that's for you.
Thank you, man. I appreciate it.
I'm so excited for the Hot Pocket.
That's not him.
You kind of live for those. They kind of get you through the day.
They really do, because I don't go get like actual lunch. I'll have a Hot Pocket, and then I have to go to work, so I'll eat something at work when I get there, like some fettuccine alfredo, and then I'll
Where do
eat
you work?
Carrabba's Italian Grill.
I don't know where that is, Is
Aurora.
is it nice?
The food's good.
I need like a nicer area, restaurant in the area to take my grandmother to for her birthday.
It's Italian.
Congratulations on multiple distractions simultaneously.
Oh, you said class is over.
My God, did I?
No.
No, I didn't. They're doing the damn droopy dog thing. Let's do one distraction at a time.
No, speak more. Video.
Damn it, Noah.
Wait, no, here's a compilation of his greatest moments.
Oh my god.
Is it the white dog with black ears?
Yes.
Isn't he from like Looney Tunes?
Yeah.
Speak! Stop
I
walking!
have a question.
Yes,
What is the
thank
impo-
you.
What is the importance of the residue? What is it like?
It will allow us to rock integrals with incredible ease. We will cover a thing called the residue theorem.
I am all about easy integrals.
The residue is 3 over 4?
The residue is this number here.
Oh.
The number on top of the,
Okay.
yeah.
Yeah.
You couldn't find it, could you?
I could find it, but none of it was good enough audio quality. It was all like, and also, he doesn't talk a lot, so a lot of it is just me looking for parts where he talks to get him talking for like 3 seconds, and I got bored.
It definitely has consumed some time.
I'm usually the one who consumes.
Well done. Well done. You got me. All right. Yeah, let's just bring it. I'm not going to say anything else. But you've got lots of practice. Please start early. Please start early so we can come in and talk about problems on Wednesday. Does this sound okay?
I think so.
You have a question? Already?
Yes.
Cool.
So when we're doing the expansions, if we're doing like Taylor series looking expansion, it would be valid if whatever was in the box is less than 1.
Yes, ma'am.
So that's something we'd have to look out for. And then we'd have to make sure that that kind of is similar to whatever inequality we're extending.
Yes. Yes. And when you see this, so let's say when you've got your Laurent thing and it looks like this side of it, you want to think of that as this, that is divide both sides by r. You're going to go backwards from what I'm doing here, actually. That's true. And then flip both sides, and you get. So when you see this, you're gonna want to force this into it, and then work your way back. Yeah, that'll get you there.
So let's say I have one over z minus 1 squared is z minus 3, and I wanted to do something centered at like 2. Would I have to multiply 2 Laurent series together, or?
Yeah. So so let's do that really quick. So like this guy, but at 2.
Yeah.
So you'll have a radius of 1. So let's see here. And actually there's no lower cap because 2 is not a problem. So this probably doesn't require a Laurent series.
Okay.
If we don't have to stay, if the singularity isn't where we're centered, then the Laurent probably won't. I think you had asked this earlier, but yeah, I don't think we'll get a Laurent series unless we're centered at a singularity. Because we need to avoid it, so we need to have a little region around it to keep us away. Cool. Yes, but to do this now, what I would do is I would write this as z minus 2 plus 3 squared, and then z minus 2 minus 1. And there's my z minus 2. Now I gotta get that to be a 1, and I'm good over here. And I might have to multiply series together, term by term.
That doesn't sound fun.
Yeah. Or do a partial fractions expansion first. That could work. That actually is probably better.
Yeah, you should do that.
Yeah, I think that's the way to go. Lou, you had a question?
Yes, I had a question about the homework. How many
Yes.
terms do you want? Because most of it's expanded.
Just,
Like how many do
17.
you want?
I don't want you to write 17 for sure.
I'll do it.
Oh God.
I'll do more.
Not that I'm trying to do like less. I just
No, I mean,
Like,
enough
what we
to indicate the rhythm on the principal and analytic parts. So two,
Okay.
three on each side.
okay.
Thanks. Good stuff, friends.
Hey,
Good time. I'll miss y'all.
same time on Wednesday.
Yep, same time on Wednesday, and
And Dr. T
sometime next
definitely won't curse.